Hello, and welcome to this talk, Every Strand Counts, Physics and Rendering Behind Frostbite's Hair. My name is Taillandier, and I am a senior software engineer at Frostbite Stockholm, working within the physics domain. I'll be covering the simulation section of this talk.
And hi, I am Valdes. I am a rendering engineer in the Frostbite Stockholm rendering team, and I will be covering the rendering section of this talk.
Before entering the details of the agenda, we thought we would give you a first taste of the current status of our Strand hair technology. Here it is. We should mention that what you see on screen is a work in progress. FIFA is only exploring the feature with us at the moment. The pictures you see on screen may not represent the final game. We have targeted the next generation of consoles for this technology. But that being said, this footage has been captured in-game. We'll start our presentation by discussing the difference between hair cards and hair strands. Then we'll go on to describe our simulation of strand hair. Then John will take you through the new aspects of the rendering parts of our technology. And we'll finish by illustrating our technology by taking a look at 3 specific use cases that we worked on recently. 45 minutes is unfortunately too short a time to go into all of the details of our technology. So if you are interested to learn more, please refer to our SIGGRAPH 2019 presentation, as well as our public blog posts. We won't have the time, unfortunately, to look into how authoring is done for strand hair, but we firmly believe that this is definitely an improvement to hair cards. Strand hair allows content creators to iterate on hairstyles in a matter of minutes rather than hours. Finally, we won't have the time to discuss performance today, but we can tell you that this technology allows us to support several characters on screen at the same time, in real time, on a sports title today. First, we should explain the FIFA context of that presentation. We've been working on strand hair for about 3 years within Frostbite, but in the last year we've worked very closely with FIFA to try and achieve a really game production quality for authoring, simulation, and rendering of that feature. And we are very proud of what we achieved today, but we would never have been able to do that without the great help of FIFA engineers and content creators. That being said, we should mention that this is just an exploratory feature for FIFA right now. And all of the assets that you will see today may not represent what you will see in the final game. For real-time scenes, the current standard in the game industry is to use the so-called hair cards to represent a head of hair. A common workflow for content creators is to generate the strands in the digital content creation tool, and then model a number of meshes, the hair cards, to represent the strands. The hair cards will then be textured by projecting the strands onto them. You can see an example on the image on the left. The right-hand side picture shows the meshes onto which the strands have been projected. On the left-hand side of the picture, it's relatively easy to notice the strands have been grouped together on the surface of a card by projection. The higher the number of meshes, the better the illusion of simulating and rendering a real head of hair will be, but the more expensive the asset will be. Using hair cards is relatively cheap computationally, but reaching high quality in either rendering or simulation is difficult and can be very time-consuming for content creators. As shown on the image on the right, strand hair takes advantage of a representation that was mostly used in offline rendering, That is, that both simulation and rendering is being done at the individual hair strand level. While it is quite challenging to make this approach performant enough for real-time, content creators find that authoring strand hair assets is easier and much faster than authoring hair cards. In terms of data, strands are important to our engine as NURBS. Our data pipeline creates a set of points uniformly positioned along each strand to represent the curve, a process called tessellation.
One thing we have realized is once you get used to seeing strand-based hair, it is easy to forget how much better it looks compared to the hair cards we had before. So here is a comparison of how it used to look with the cards versus how it looks with strand hair. We think it looks quite a lot better. As another example, here is a very short hairstyle which you wouldn't think it would improve much with strand hair, but the difference is still pretty big thanks to the nice shading and all of the subpixel detail we can preserve with this technique. And here is another example with curly hair, which also looks much better than before. Cards are made of triangles, so they have a lot of trouble trying to approximate a shape as complex as curly hair. And strands can do a much better job at that. And finally, here is a comparison in motion. Seeing these two systems side by side is a good way for us to remind ourselves of how much a difference strand hair can make on how characters look in our games.
Alright, let's now go over an overview of the simulation. To start with, let's discuss where the data is coming from, where those strands that we see on screen are actually coming from. As discussed before, the strands are important in our engine as NURBS. In our offline data pipeline, we will tessellate these NURBS in a number of points, which means that we will basically replace the representation of the curves from NURBS into a number of segments. And these new strands formed of points, segments, are the render strands, where we will actually render on screen. Once this is done, we will actually select a number of render strands to become the simulated strands, what we will animate. A high number of points along the curve will increase the quality of the simulation, but costs will rise. Tessellation is configurable per asset and ranges from 3 to 32 points per strand. In a nutshell, what the simulation and interpolation aims at doing is to displace the render strands, shown in red, by interpolating the position of the simulation strands, shown in green. Our simulation is entirely GPU-based, and we use an Euler Lagrangian approach, which I will explain in more details in the following slides. As a helping guide, here is a graph showing the data flow throughout the compute shaders of the simulation. This is an overview and doesn't represent exactly all of the compute shaders or all of the data that we are using in the actual simulation. But hopefully this graph can be helpful in understanding, in broad strokes, what is actually happening in the simulation. As you can see, we'll start by skinning some of the points, then we'll integrate all of the simulated points. We'll then go to solving those points, actually solving the constraints that are acting on those points, and we will interpolate the render points from the simulation points. The first part of the simulation is the skinning shader. Here, we'll perform a classic skinning operation on the first segment of each simulated strand. Usually, the strands are skinned to the head joint. We find that skinning the first segment, and not just the first point, is very useful to help the simulation maintain the authored shape. In the picture behind me, you can see a debug rendering of a head of hair where the points of the first segment have been colored in red, and the rest of the points, the simulated points, are colored in green. Here is a video showing the difference between a simulated head of hair and a skinned head of hair. As you can see, the difference is quite noticeable. That being said, on shorter hairstyles, such as the ones shown behind me now, skinning is definitely sufficient. In addition to supporting classic skinning, we also allow the strands to be driven directly by the displacement of the triangle they are the closest to on the head mesh. This option is slightly more costly, but allows for strand hair to follow facial animation very closely. This doesn't preclude anything with regards to simulation. So to do so, we find the closest face in the head mesh, for each of the root points. The pictures behind me are a debug rendering of this operation, which is relatively costly and is performed offline. The picture on the left shows the head mesh, and on the right, the first segment of each strand is displayed in green. Each face, which has been selected by a root point as the closest, is displayed in blue. Finding this face is also a way to find the UVs and barycentric coordinates of the strand roots. We will extract the UVs and barycentric coordinate from the face. The UVs will then be useful for numerous reasons. For instance, anything related to textures with regard to rendering, such as like widening the hair rendering or finding colors to apply to the strands. In the runtime, to do the actual skinning, we then simply replace our classic skinning shader with a displacement of the first segment of each of the strand at its barycentric coordinate on the displaced face. In the video behind me, you can see a beard using this skinning technique. Let's explain the integration in more details. We are using a position-based dynamics solver coupled with a Valdes integrator. In our solver, as is usually the case in games physics, we don't solve all dynamics as one coupled system. Instead, we speed it up in two steps: integration and constraint solve. In the integration, we consider the points as free bodies. All constraints between the points are ignored, and we simply apply external forces which don't rely on direct coupling between the different points, for instance, gravity. The time step, or delta time, that will be communicated to the integrator can be variable, but I won't go into the details of variable delta time today, as I don't really have the time to about all of its complexities. As for normal Valdes integrators, our method uses the previous positions of the points and their current position to determine their ballistic motion. This ballistic motion, together with the external forces that are applied on each of the points, will be used to compute a new position. However, it's also at this stage that the Euler part of our method is coming into play. The external forces are not only computed from gravity, but also from several physical quantities that have been accumulated over grids prior to the integration shader, such as the average velocity or the average density, which will be used to compute friction and volume preservation, as we'll see in the next few slides. An important driver of hair behavior in real life is friction. However, modeling friction between each simulated strands is too costly for runtime computations. Instead, we use a grid-based approach, where the idea is basically to average the displacement of the points in each cell to get a displacement per cell. Then, the friction parameter of the assets will be used to determine per point how much of the ballistic motion of the point and how much of the grid displacement will be used to compute the point final position. In the two videos behind me, you can see the same character with normal friction on the left and with high friction on the right. Notice how the strands are moving in bulk motion on the right, whereas the movement of individual strands is more noticeable on the left. And in this video, you can see a debug rendering of the grid containing the average velocities. The velocities in X, Y, Z correspond to RGB colors. In a similar way, we use a density grid to mimic volume preservation, the density gradient at each point acting as an external force. Try and illustrate what volume preservation does In the video displayed behind me, you can see the same asset I used before, but with a volume preservation factor cranked up to 11. Notice how the hair tries to maintain a larger volume compared to before. This is the volume preservation acting as an external force to try to maintain that volume. The integration step is now done, and the result of the integration is now used as input to our projected gauss-seidel solver. As is common in games physics, we now need to solve everything we left out during the integration as constraints. When we consider a constraint, we simply move the affected points so that they satisfy that constraint. Since constraints fight against each other, we need to repeat this process. In other words, we solve the same constraint many times, iteratively, in each same step. I'll detail each of the different constraints in the next few slides. The stretch constraints will try to maintain the original segment length by pushing apart points that are too close to each other, or by bringing together points that are too far away. The local shape constraint is probably our most interesting constraint. I'll give you a quick introduction now, but we'll go into more details later on in the presentation. The role of the local shape constraint is to maintain the authored style. And to do so, the constraint will try to maintain the orientation each segment has with its parent. As for the stretch constraint, both parent and child are displaced by the constraint. Global length is a constraint that we use usually with a quite low factor, as it's far from physical, but it's quite useful to fix up stretching sometimes. It works simply by bringing up a point toward its parent. The parent is not moving in that case. This kind of follow the leader approach can lead to bouncy behaviors if used with a too high factor, but at low factors it can be sometimes useful to combat high stretching. Finally, the iteration ends by displacing the points that are inside colliders. In the picture behind me, you can see a sphere and a plane example, but we also support capsule colliders. The number of iterations that we are doing is a parameter on the asset itself, and usually depends on the number of segments on the asset. Usually, it ranges between 3 to 10 iterations, but it can go higher than this. During the interpolation step, we will loop through all of our render strands and interpolate the position of their points based on 3 sim strands. These 3 sim strands and their interpolation weights are selected offline based on distance. With this simple scheme, we don't need to simulate too many strands. We find that usually simulating only 10% of the render strands is sufficient. In the asset that you are seeing on screen now, we are rendering around 32,000 strands, but only simulating a little bit over 3,000.
Now onto the rendering tech. We will now see a general overview of how this new system works, but unfortunately we won't be able to go into the gritty details about it. This presentation is just not long enough. But we are planning on doing a more in-depth presentation about the low-level rendering tech about all this, so stay tuned for that. So, hair rendering. Over the last couple of years we have showed the new Frostbite hair system in a few blog posts and presentations, but the rendering side has changed quite a lot since then, so we are going to have to explain a few things here. What we did before was render each strand of hair as a camera-aligned triangle strip, and then we relied on MSAA to produce an anti-aliased image out of that. Unfortunately, GPUs really don't like rendering very thin, long triangles, so performance wasn't very good, and image quality wasn't that great either, to be honest. The image you can see here is a typical example of this technique. It is better than what we had before with the hair cards, but it is still a far cry from what you would see in a movie, for example. And so we've been working to improve on this, and we have arrived at a completely different architecture that improves on both performance and image quality, as you can see here. The core of this new system is a new compute-based software rasterizer. Using a software rasterizer gives us a lot more freedom to implement things however we want, and has allowed us to get two very important features for hair rendering. First, because we are implementing rasterization ourselves, we can calculate anti-aliasing analytically, so the hair comes out of the rasterizer perfectly anti-aliased already. We simply calculate how much of the pixel is covered by each strand and consider that the alpha value for the strand in that pixel. Having properly anti-aliased input data removes a lot of noise from the final image. But having the anti-aliased strands wouldn't really work without the ability to then properly compose them. And this is where our second feature comes into play. Because we're using a compute-based software rasterizer, we cannot rely on the hardware to blend our hair fragments together into the final image. And so we are forced to implement a custom blending strategy. We decided to use that opportunity to try and implement a form of order-independent transparency using a per-pixel transmittance function. And this turned out to work really, really well. It allows us to properly and efficiently compose semi-transparent hair strands and get really nice results, as you can see. Also, that image smoothness is preserved under motion, so we get really smooth and soft flowing hair with very little noise. Now let's go into an overview of our new hair rendering pipeline. It begins with the hair simulation providing us with the position, orientation, and velocity of each of the strands. This data goes first into the shadow rendering, where we render hair either to normal shadow maps or to deep opacity maps. You can check the SIGGRAPH 2019 presentation we did for more details on this. After that, the strand data goes into the coarse rasterizer. This piece of code bins incoming segments into screen space tiles, generating a list of segments per tile. It also does a coarse z-culling pass to discard any segments behind geometry. Finally, it generates a binary visibility value for each segment of each strand, which we can later on use to check whether a segment is visible or not. At this point, we run the shading pass. This shading model that we are using hasn't changed much since we last presented it at SIGGRAPH, and it's based on a Marshner model. What has changed, though, is the way that we invoke it. Instead of calculating the shading once per pixel, or even once per fragment because we were running with MSAA before, we now split each strand into a few shading points and we only shade those. This is what we're calling strand space shading, which is pretty similar to texture space shading, but in one dimension instead of two. This allows us to easily control the number of points that we shade. In our tests, it was very difficult to tell the difference between shading every single fragment and shading only 2 points per segment and interpolating between them. The shading is quite expensive, so for close-up shots this has resulted in quite a big performance improvement over the old system. For now, the number of shading points per segment is hard-coded, but we are working on the ability to control this based on camera distance. We expect this to be finished in the next few weeks and should give us even better performance on wide shots. The shading pass also uses the visibility value the coarse rasterizer generates, so that only segments that are visible to the camera get any shading, and we don't waste time shading invisible segments. Once we have the strand space shading, we invoke the fine rasterizer. This is the part that does the actual rasterization of our hair. It grabs every one of the tiles generated by the coarse rasterizer and iterates over all their segments, rasterizing them one by one. It checks which pixels in the tile are covered by which segments, and it generates a final color value for them. It does this by first calculating the analytical anti-aliasing for each strand, combining that with the shading information in the strand space shading buffer, and finally applying the order-independent transparency to combine the color of all the segments into the final one. I'll talk a bit more about the OIT system later on. With all this, it generates the final color and depth information for each pixel and puts them into two output render targets. Once we are done with the rasterization, we also need to generate motion vectors for hair. These are extremely important for TAA and motion blur to work correctly. What we do is use the depth information at each pixel, reproject that into world space, and grab the hair velocity at that point from the hair velocity grid that the simulation generated. With this, we get an approximate velocity at each pixel, and I say approximate because the grid is not super high resolution, so the velocity is not perfect, but it's still good enough for what we need. Doing this allows us to avoid keeping around the previous position of each hair so that we can calculate the perfect velocity, which is quite a lot of memory savings, and also it was faster this way. Once we have the motion vectors, we combine the color and depth hair buffers into the main color and depth render targets. And at this point is where the normal rendering flow takes over and applies TAA, depth of field, motion blur, etc. to produce our final image. As I have mentioned a couple of times already, correct compositing of semi-transparent strands is crucial to get nice looking hair. When we decided to attempt to use order-independent transparency, we prototyped several different ideas, but in the end we came up with something custom which fits the way our rasterizer works really well. First, the coarse rasterizer keeps track of the closest and furthest distance from the camera to a hair segment in each tile. Then, in the fine rasterizer, we take that range and split it, creating many slices along the whole depth of the tile. Now the rasterizer loops over all the segments in tile and generates color fragments for each covered pixel and stores them in a big buffer. But it also stores a pointer to that data in a linked list for each of the slices we have in the pixel. This way, once we are done generating the color value for all the pixels covered by each of the hair segments in the tile, we can go through the slices in front-to-back order and correctly blend together all the fragments we generated before. As the rasterizer goes through all the slices, it calculates the accumulated transmittance function for the pixel and uses that to blend the next fragments in line. In the case where we have more than one fragment stored in a slice, we have no extra depth information to decide in which order to blend those fragments, so we just alpha blend them. This is technically incorrect, but the slices are extremely small in world space, so we can only fail to sort things correctly by a matter of millimeters, and the general volume of hair will still be sorted correctly. Or at least correctly enough that the artifacts are extremely difficult to notice, and the hair volume will look nicely blended together. Given that a hair model contains tens of thousands of strands, it wouldn't make much sense for us to render and shade all of them when a character is only covering a very small portion of the screen. We wanted to somehow render fewer strands as we move away from a character, but we didn't want to do anything that would require more manual work from artists. We decided to try to render only a certain percentage of strands based on screen coverage. We debated whether to mask out some strands or come up with a complex algorithm to choose which strands to render, but in the end we came up with a nice and simple solution. We just randomized the order of the strands and then rendered the first n% of them. This required just a few tweaks in the rendering code and gives us a LODding mechanism that scales linearly with distance and is almost invisible to the naked eye.
We'll now discuss 3 different use cases, which led us to improve our technology, both on the simulation and on the rendering side. We'll start by talking about the ponytails, then curly hair, and finally headbands. It's with this type of assets, ponytails, that pendulum effects are showing the most. As such, it's important that the behavior matches what we see in real life, and that the ponytail is allowed to rotate freely, no matter the head orientation, while maintaining its authored shape. This is for this type of asset that we spend a lot of time improving on our local shape constraints. The important thing to realize is that the constraint will try to maintain the segment orientation in its parent space, not in world space. So prior to the solve step, we actually spend some time computing the target of each segment in its parent space. And this is what the actual local shape constraint will try to match. The video that is playing now behind me maintains the shape in local space. But if we were to maintain in global space, this is what would happen. We could summarize the difference between the two by saying that maintaining the shape in local means that we compute the constraint angles with respect to the current position, while maintaining the shape in global would mean computing the constraint angles with respect to the authored position.
Ponytails also turned out to be an unexpected problem for the rendering side. As I explained before, the fine rasterizer works in tiles. It launches several parallel independent processing units, which we call processors, and each of these processors consumes tiles from a global queue. The order in which they consume these tiles is pretty much random, so we expected some variation in the timings from frame to frame, but the timing variation we saw was much higher than we expected. Some frames were taking almost twice as long as others, and we had no idea why. So we looked at our debug data, and we saw this. Some tiles were taking a lot longer to process than others. If a tile contained many segments, it took longer, which is logical. But if one or two of these very expensive tiles happened to end up at the end of the queue, we ended up with just a couple of busy processors while the rest of the GPU sat idle, having nothing to do. A simple fix helped a lot. Just pre-sort the tiles in the queue by the number of segments in each of them. This way, the most expensive tiles get processed first, and at the end of the queue we have many small tiles which are very easy to distribute. This meant more stable timings and a significant performance improvement. That is, at least until we have a ponytail on screen. If you think about how a ponytail works, you are grabbing almost every strand of hair in your head and putting them all together. If a human head has about 100,000 strands of hair, the start of the ponytail is a very small area that contains pretty much 100,000 strands of hair. And that means a few screen space tiles will end up with dozens of thousands of hair segments each. So we came up with a way to alleviate these issues. Instead of binning just in 2 dimensions, leaving us with screen space tiles, we added depth clustering, giving us effectively voxels. The advantage of this is that the fine rasterizer can now process each cluster in front to back order, and as soon as it reaches full opacity, it can stop processing any more hair segments, because segments behind something that is already opaque are not going to be seen anyway. We can do this in a per pixel level, but also on a per tile level, so when the full tile is opaque, it can stop processing segments for the entire tile. This resulted in a more than 4x performance improvement in our worst case scenario with the ponytail.
Curly hair assets, such as this one, are not easy to solve. One expects to see some motion in the strands, while the entire head of hair should maintain its shape. In terms of tuning, it is quite different from the ponytail asset which we just saw, or from longer hairstyles. For this type of hair, we rely more on friction, volume preservation, and really high values for our local shape factors. Actually, the local shape constraints had to be improved again for this specific asset to support for those very curved strands. And we had to introduce quite aggressive stabilization techniques in that case. In this asset, we are also relying a lot on interpolation to see bulk motion. We don't really need to see the individual strand moving as long as the bulk motion is correct. So we are actually only simulating 2% of the render strands here.
Since we started working on this project, we had considered very curly hair as one of the biggest challenges for this tech. We just didn't think it was going to work very well. To get nicely curved hair, we would need to subdivide it a lot, but then that would increase the simulation costs massively. Ideally, we would do something like the tessellation stage on the GPU, but it wasn't really clear how to do that with our architecture and still maintain good performance. But once we had our software rasterizer, we realized we had a lot of freedom, and we could actually try to do something like this. So our idea was, what if we treated the hair points as if they were the control points of a spline? We could then take that spline and subdivide it however much we wanted. And we could do that in the inner loop of the rasterizer itself, keeping it very, very fast. So we tried that, and it worked really well. We could now subdivide each original hair segment in the rasterizer itself, creating soft curves where we had a lot of harsh angles before. This, happily, improved the look of curly hair characters without much of a performance cost.
We didn't have any support for proper headgear so far. And as discussed earlier in this presentation, we only skinned the first segment of the strands. As such, when we were presented with an ask to support a headband character, it seemed difficult to achieve. Our first attempt was to ask the content creators to separate the asset in two: the strands below the band would be simulated as usual. The strands above the band would only be skinned. It produced this result. Which is nice, but we felt we could do better. We tried a simple approach, which turned out to work very well, even if we had to fix a few corner cases for it. By skinning the last point in the strand, as well as the first segment, for specific parts of the assets only, and by adapting the simulation to support this case, we managed to obtain the result you can see behind me now. Notice how the hair strands on the top of the head are now moving slightly. We are pretty happy with this result, and we hope that we can add new features like this in the future.
For rendering, the headband exposed another small issue within a list of very big problems when trying to render semi-transparent objects like hair in real time. When rendering hair, we can choose at which point in the frame we want to compose the hair into the main render target. Ideally, we would compose each hair object back to front, sorted correctly with the rest of the transparent objects. This is impractical because of performance reasons, so we chose to render hair after the transparents and live with the wrong sorting in some situations. However, this still leaves us with a big choice, whether to compose hair before or after the TAA pass runs. Our rasterizer produces perfectly anti-aliased hair, so in theory we shouldn't need TAA to do anything to it. But if we render after TAA, we run into a problem. For TAA to work, we have to jitter the camera randomly every frame. Then TAA accumulates the last few frames and produces a smooth, jitter-free image. So we could render hair after TAA without jittering and we should be good, right? Well, TAA does smooth out the jittering in the color buffer, but we don't really have a good way to do that with the depth buffer. What this means is that if we render after TAA, our hair will not be jittered, but it will be depth tested against the jittered depth buffer. And this results in z-fighting in the intersection between hair and geometry, like a headband, for example. And that's not everything. Depending on exactly at which point in the frame we compose hair into, we can get good depth of field or good motion blur or good sorting, but we just can't have everything at once. Every single way we have tried to compose hair requires a trade-off. In the end, we exposed the choice to the lighting artists. They could choose a resolve method that would have good depth of field and bad motion blur, or one that has good motion blur but bad depth of field. This is less than ideal, but it has allowed us to hide the most glaring issues pretty well. The bottom line is real-time rendering of semi-transparent objects is a very hard problem. You can check this nice talk by Morgan McGuire for more information on that.
We are reaching the end of our presentation, and it's time to conclude. Today, we shared our latest advances in real-time strand hair rendering and simulation, and gave you a sneak peek at how much the character visual quality bar could be raised in games. Using strands not only enables for a much better rendering and simulation compared to hair cards, but also allows content creator to iterate quicker to produce better assets. We strongly believe that strand hair is a step change in authoring, simulation, and rendering for games. That being said, we still have a lot of work to do to support the large variety of hairstyles out there. For instance, we don't have proper support yet for braids, plaits, or dreadlocks. We don't offer a solution to apply dynamic conditions on hair, such as wet hair or muddy hair. And we don't have a native support for attachments, such as ribbons or jewelry, for instance.
On the rendering side, there is also a lot of work left. For starters, the hair shadowing techniques we are using are fine in most cases in FIFA, but quality and performance could both be better, so we will keep working on that. Also, as I mentioned earlier, doing transparency correctly is hard, so we need to work on better ways to combine hair with other transparent objects, and also on how to make hair work well with all of the post-effects passes. Still, we are extremely proud of what we have achieved in the last year, and we hope you liked it too.
Such a large project has obviously a lot of people involved, but we would like to specifically thank the members of our teams who work with us on the Strand Hair project. We would also like to thank several members of the FIFA and EA Create teams who have been instrumental in making this project a reality. Thank you. And thank you for your attention.